So hello everyone, welcome to the HPL seminar this week. I am pleased to introduce our speaker today, Arash Khassetarash. Arash started his undergraduate in 2008 in mechanical engineering at the University of Tabriz in Iran. During his undergraduate, he worked on a project of modeling and control of car suspension based on 11 degrees of freedom vibration model and achieved his bachelor's degree in 2012. He then started his master's at the same university under the supervision of Dr. Riza Hassanejad. Arash's master's thesis was about the vibration analysis of human soft tissue for fatigue detection and optimum design of footwear parameters in running. And then he achieved master's degree in 2014. Then in 2017, he started his PhD in kinesiology here at the University of Calgary under the supervision of Drs. Brent Edwards and Guillaume Millet. Arash has been working on investigating strategies to reduce the harmful effects of downhill running, and he is planning to graduate next year. He has also work experience where he conducted various projects focused on the effects of vibration parameters of footwear on muscle activities during walking. He also worked for a car industry as an engineer at the Azar Motor Mobile. Aside from his work career, he did not mention in his bio sketch, but I actually have something that I would like to share with everyone here. It has been largely announced that Arash is going to attempt to break the man's Guinness World Record by completing 80,000 pull-ups in 24 hours. So good luck, Arash. Today, he is going to share his part of his thesis work entitled as Neuromuscular, Biomechanical, and Energetics Adjustments following repeated bouts of downhill running. All yours.
Thank you, Sawan, for the introduction. So this is a photo from Great North Run in 2013, and this is till today one of the best half marathon races I've seen. In this race, there's an interesting part at the end of and at the last mile of this course. There's a steep downhill that this photo is taken. Here in this steep downhill, Bekele, this guy, started to speed up, and he created a gap that even the gap was so long after that that even Mo Farah with that deadly finishing kick couldn't close that gap. So it's quite a skill to run downhill and speed up without incurring too much damage to your body. I believe Bekele could do it because of his long experience with cross-country running. With that introduction, let's talk about downhill running today. So we know that the biomechanics and physiology of lever running have been widely investigated, but the literature when it comes to downhill running is scarce. Downhill running is important and becoming even more important since mountain ultramarathon races and trail running events occurring during the past 2 decades specifically, and also recreational running on city terrain consists of long sections of graded running. So unless you're running on a flat track or maybe on a treadmill, you will probably never run on a completely flat surface. Downhill running specifically has been used as a model of exercise-induced muscle damage. And there's a specific reason for that. So this is a typical example of joint power during lever running, the solid line, and downhill running, the dashed lines. As you can see, during the first half of this stance, there's a huge energy absorption going on, specifically in downhill running compared to lever running, and it's more obvious in the knee. Assuming a part of this energy absorption causes muscle damage, it's been classically shown that prolonged downhill running produces high amount of this muscle damage. And conceptually, the paradigm can be represented like this, as a large eccentric contraction or negative work causes muscle damage, and then that causes reduced stability of muscle tendon units to resist tension, and then uh, itself causes more muscle damage, and this is a positive feedback loop. So the amount of muscle damage might be dependent on several factors. For example, the higher the duration of downhill running, the more the muscle damage, the higher the intensity in terms of slope and speed, then the muscle damage is higher. And it is believed that if the runners have a resistance training background, then the amount of muscle damage is going to be smaller. So one of the consequences of this exercise-induced muscle damage is the reduction in strength. And specifically, we have an example here of a study that they did 300 maximal eccentric knee extension, and then they looked at the maximum eccentric torque. Right after the bout, there was a huge reduction in this eccentric torque, close to 40%, and then it gradually increased, but the strength loss persisted at least for 3 days after the initial bout. The story is the same when we look at the whole body exercise, like 30 minutes downhill run, and the isometric torque that they looked at, and the extension torque they looked at, there was a huge reduction, over 20% right after the downhill run, and then this reduction persisted days after the initial bout. So there is a strength loss right after, and then there's a persistent strength loss days after the exercise-induced muscle damage. But when we talk about exercise-induced muscle damage, we should consider a very important phenomenon that is known over half a century now. This phenomenon is called the repeated bout effect. And it says that performing an initial bout of eccentric exercise produces a protective effect such that the repetition of the same exercise becomes less severe. This is a classic definition of repeated bout effect. You probably experienced this, specifically with this pandemic going on and gyms closing and opening. When you go to the gym after a few months and you do your first squat session, you get very sore the day after. But if you repeat the same bout a week or 2 weeks later, you get less sore. That is the repeated bout effect. Here we have an example of a 40 minutes downhill run, two times 40 minutes downhill run, separated by 3 weeks. This is the first bout, and this is the second downhill run. We looked at indirect measures of muscle damage. One of these indirect measures is muscle soreness. So right after the downhill run, there was an increase in muscle soreness, and this increase even exacerbated in 1 or 2 days after. While during the second downhill, there wasn't much increase in muscle soreness. They specifically looked at the quadriceps soreness. And then another indirect indicator of muscle damage is creatine kinase activity in serum. And an increase in creatine kinase activity shows an increase in indirect measure of an increase in muscle damage. After the first downhill run, there was a huge increase in CK, while after the second downhill run, there wasn't much. So this basically shows the repeated bout effect in downhill running. And we know that this protective effect can last for weeks and sometimes even months, but it won't last more than 3 months. As of mechanism that causes this repeated bout effect, there's been a lot of studies in the literature, and this is a nice picture from a review by Hildal and colleagues. They concluded that multiple mechanisms work in concert to produce this repeated bout effect. So after this eccentric contraction bout, you get neural adaptation or maybe muscle tendon complex adaptation, better inflammatory response, and extracellular matrix remodeling. But the question that we are specifically interested in this study is the biomechanics of downhill running and the relationship with the repeated bout effect. So we came up with these questions that how do running biomechanics change during prolonged downhill running? We hypothesized that prolonged downhill running will cause muscle damage, and that will cause a reduced ability of muscle tendon units to resist tension, and that in turn will cause reduced joint stiffnesses, and that will translate into increased contact time and reduced flight time, which is a specific style of running known as grounded running. And then for the second part and second question, we asked how does the repeated bout effect influence changes in running biomechanics during prolonged downhill run? We hypothesized that the repeated bout effect will cause more resistance muscle tendon units, and then this in fact in turn will cause less muscle damage during the second downhill run compared to the first downhill run, and then that will cause less reduction in joint stiffness and less change in spatiotemporal parameters and less transition to grounded running. To answer those questions, we came up with this protocol of 30 minutes downhill run bout separated by 3 weeks. First of all, we did a familiarization session with downhill running and then neuromuscular fatigue assessment. And then on a Monday, the participant did the first downhill run, and then 3 weeks later, they did the second downhill run at the same time of the day. So the duration was 30 minutes, and then we kept the speed constant for all participants at 2.8 meters per second. And the grade was also constant at 11.3 degrees to have an idea of how steep this is, specifically for those people who might not run that much. So this would be a slope of the hospital hill in Calgary, or a bit less steep than Nose Hill Park. We recruited 11 male recreational runners for this study, and we measured ground reaction forces and 3D motion data. And right before the downhill run and right after the downhill run, and every day up until a week, we looked at neuromuscular function, specifically in the knee extensors. And then we also, to show that how damaging the bouts were, we looked at the blood creatine kinase activities up until 4 days after the initial bout. And then we also looked at the perceived knee extensor soreness in squatting position to assess the indirect measures of muscle damage. So here we take a look at the indirect markers of muscle damage, first of all. So these are the results. The maximum voluntary contraction and knee extension reduced up until 16% in downhill running 1. And then this reduction was smaller in downhill running 2. So we had a repeated bout effect in isometric torque in the extensors. And then we looked at this soreness, perceived soreness measure in squatting position. Right after the downhill run, there was a huge, the first downhill run, there was a huge increase in this soreness. And then this soreness persisted at least after the initial bout. After the second bout, there was not much of a soreness in quadriceps. So there was a repeated bout effect here as well. And then we looked at the creatine kinase activity, and there was an increase in CK activity right after the first downhill run, and then this increase became more in 48 hours, and it persisted up until 96 hours. During the second downhill, there wasn't much of an increase in CK activity. So all in all, with these results, we can conclude that the initial downhill run was damaging and a RBE was in fact occurred. So now let's move on to biomechanics. The instrumented treadmill gives us forces parallel and normal to the surface of the treadmill. So I first transform these forces to horizontal and vertical directions, and then we get ground reaction forces, vertical and horizontal component. In order to calculate the center of mass work, we need to calculate the power. I use this equation of basically the dot product of force and velocity. We can get the velocity in vertical and horizontal direction by integrating the forces. And then we get a graph like this for power curve, and we can look at the energy absorption and then energy generation, or negative and positive work. And regarding the hypothesis about the stiffness, we can first calculate the leg stiffness. I think you are familiar with this McMahon 1990s model. This is a famous model of human running, modeled human running as an inverted pendulum, where is attached to a spring, and then body mass is modeled as a point mass at the top of the spring. It assumes that while the human is running, this mass moves downward and forward. This model has some parameters as delta y as center of mass excursion during the contact time, maximum excursion, and then the delta L, which is basically how much this spring is compressed. And then we can calculate the leg stiffness as the maximum ground reaction force divided by the maximum leg spring compression. And then this delta L can be calculated over here, but the only important thing is that it depends on the speed and contact time and the leg length. And now we can move a little bit forward to look at more detailed calculations as joint quasi-stiffness. By performing an inverse dynamic routine on 3D motion data, we can get the joint torques, and then we can also get the joint angles by 3D motion data. And the idea is that lower extremity joints can be modeled as torsional pseudo springs. They're not real springs, but they can be modeled as pseudo spring when you consider the joint moment to plot the joint moment in front of the joint angle, and you get a graph like this. And if you regress a line from foot strike to mid stance, or basically the absorption phase of contact, and then the slope of this line will basically be the delta t over delta theta, or changes in joint moment over changes in joint angle, which gives us the knee stiffness or joint stiffness in general. This one is knee in specific. Now we can move on to the results. So we calculated the spatiotemporal parameters at the end of every minute of the run up until end of the 29 minute. And we can look at specifically the different parameters. The contact time during downhill running, the solid line, increased almost linearly up until the end of the downhill run, and it became significant in 20 minutes, reduced significantly, and it became significant after 15 minutes. And then step frequency did not change much, and duty factor also increased almost linearly up until the end, and became significant in 10 minutes. During the second downhill run, contact time increased, but the increase wasn't significant. The flight time reduced significantly, but the amount of this reduction wasn't as much as the first downhill run. Duty factor also increased, but the amount of this increase wasn't as much as the first downhill run. So there was a repeated bout effect going on in flight time and duty factor, and a somewhat transition to grounded running. And when we look at the center of mass work, the story is quite the same. The energy absorption increased during the first downhill. It didn't change during the second downhill. And the energy generation reduced significantly during the first downhill, did not change much during the second downhill. And there was a repeated bout effect for these parameters as well. And then we can also look at the steepness values. Leg steepness linearly reduced up until the end of the run, and it became significant in 20 minutes. The story goes the same for knee stiffness, as it became significant in 15 minutes, and the ankle stiffness as well. It became significant in almost 5 minutes after the first downhill run. And after the second downhill run, the stiffness values did not change. And we detected repeated bout effect for leg stiffness and knee stiffness. So with that result, as we hypothesized, prolonged downhill run resulted in alterations to running form and the transition to grounded running style. Whether or not these transitions are beneficial, more studies should be designed, specifically looking at the tissue level loading. And this reduced lower extremity joint stiffness that we showed seemed to be responsible for this transition. Regarding the repeated bout effect, we showed that repeated bout effect limited this transition due to the stiffer knee joint, as we found RB knee stiffness. And considering that the joint quasi-stiffness did not change during the second downhill, purely mechanically speaking, the muscle tendon unit or joint specifically seemed to be better resisting tension during the absorption phase as we modeled joint stiffness. However, there might be some neural adaptations going on as well. For example, a better co-contraction response, which will result in a better knee stiffness, stiffer knee. With that, we looked at we designed the second part of the study, and we looked at the neuromuscular function and its relationship with the RBE. I already showed you this protocol. We had neuromuscular fatigue assessment before downhill run and after downhill run, and every day after downhill runs up until a week. Same thing after downhill run 2. And the question was, how does the RBE affect changes in neuromuscular fatigue? So I'm going to go on and talk a little bit about the methods. For assessing the neuromuscular function parameters in knee extension, the participant sits on this chair, as shown. A force transducer is attached to the ankle. So if the participant is doing knee extension, we can measure the force. And then we have this electrical stimulation on the femoral nerve that we can deliver electrical current to the nerve. So we ask the participant to do maximum voluntary contraction. While they're doing so, we stimulate the femoral nerve. We get a response like this, and then they relax, and we stimulate a couple more times with different frequencies of this stimulation. And what we're looking for with this setting is to look at the global fatigue as we measure with the reduction in maximum voluntary contraction. And then we can also look at the components of this fatigue that could be peripheral or central. So peripheral fatigue specifically is the fatigue that is originated from somewhere below the neuromuscular junction. I'm specifically going to represent this LFF or low frequency fatigue, which is basically the division of the dB10 over dB100, the maximum amplitude of this wave to the amplitude of this wave. So low frequency stimulation to high frequency stimulation. And this low frequency fatigue can be used as a surrogate measure of impairment in excitation contraction coupling. And then we can also look at the central fatigue component, which is the component of fatigue that is originated somewhere above the neuromuscular junction. And we measure it with voluntary activation that I'm going to talk about it in the next slide. So for this voluntary activation of VA, imagine that you're doing knee extension with somewhat a lower force, like 20% of your max, and then you in this case you recruit some of the motor units. If you increase the force, you're going to increase the amount of motor units that you're recruiting. If you do maximum voluntary contraction, theoretically you're using most of the motor units, but maybe not all of them. And then when you're doing this MVC, if we add more electrical current to the femoral nerve, then we can recruit all the motor units and we get a spike in force like this. Based on the size of this spike in force, we can calculate the amount of voluntary activation. So without diving any further into the details of the method, I'd like to talk about the results specifically here. So I brought this MVC as the global measure of fatigue, voluntary activation as the central fatigue, and then dB10 over dB100, which is a low frequency fatigue, as a surrogate measure of peripheral fatigue. So we measured this parameters before, after downhill, and every day after downhill 1 and 2. After downhill 1, the global fatigue MVC reduced by over 16%, and then this reduction persisted at least 2 days. It came back to normal in 3 days. And the voluntary activation also reduced by a huge margin of 7% after the first downhill run, and it gradually came back to normal. And the low frequency fatigue also reduced by huge margin up until 24 hours, and then came back to normal. During the second downhill run, after the second downhill run, also the MVC reduced, but this reduction wasn't as much as the first downhill run, and also it came back in normal in 24 hours. So we detected a repeated bout effect in global fatigue and also voluntary activation. It did not change after the second downhill run, and also we detected a repeated bout effect for voluntary activation as well. And low frequency fatigue showed the same result as downhill running 1 and came back to normal in 24 hours. So with these results, we can say that the longitudinal reduction in quadriceps strength was partly related to the central fatigue and partly related to the peripheral fatigue. Considering that we found RB in voluntary activation, our study also supports the neural adaptation theory, saying that RB in downhill running was partly facilitated by neural adaptation. And considering the complete breakdown of running form in relatively short time, downhill running is an interesting model to study changes in running biomechanics related to muscle fatigue and muscle damage. So we have a model here that can induce large changes in running biomechanics in a relatively short time. 30 minutes is not as long time as most of the studies. And also, these changes can be mediated with prior exposure to downhill running. So if the individuals are accustomed to downhill running, this changes might not be that big. With that, I'd like to thank the participants, first of all, for their dedication for this long study. I'd like to thank my colleagues and group mates, and thank you all for your attention. And now I'll take your questions.
Thank you, Arash. Before we get to the discussion, I would like to kindly encourage you to turn on your web camera for an active interaction during the discussion period, if you feel comfortable with it. Thank you very much. If you have any questions to our speaker, please use the raise hand button that can be found when you click the icon labeled participants at the bottom center of your screen. You will see the blue icon, raise hand button, at the bottom on the right-hand side. Does anybody have any question for Arash? Yes, Tim, please go ahead.
Thanks, Arash, for the great talk. I was just curious whether you can speculate on what kind of neural adaptations you are talking about. Do you have any speculation there?
Well, there's been a lot of studies in this area as well, and they think that better harmony of the motor units recruitment, and also so during this eccentric contraction, usually the fast motor units being used mostly in the first part specifically, and it is believed that this can help in that in enhancing that response as well, using all the motor units and then better synchrony.
Okay, and these effects can occur within the 3 weeks or whatever you had between the two bouts?
It seems like it can occur even faster, but 3 weeks 3 weeks was the amount that we chose based on the studies that have been done before in different parts, in different type of exercise, single joint exercise, sometimes downhill running. We chose just 3 weeks to make sure that this will occur.
Okay, thank you.
Thank you.
Okay, Kun, please go ahead.
Thanks. Hey, Arash.
Hi.
Just a quick question. So about this, I was trying to wrap my head around, but I still haven't, how to do center of mass work in this context. So first question is, in which reference frame is this metric calculated?
Center
Is
of
this
mass
reference
work, you
frame
mean?
attached to the treadmill, I assume?
It was in the global frame, but work in general, it doesn't matter if work is a scalar. So it doesn't matter if you calculate in which coordinate system. But yeah, we did it we changed the horizontal and we changed this force in parallel and normal to treadmill to horizontal and vertical. So basically the force was changed to the direction.
Okay, and so okay, I don't believe I agree with you that work is independent of reference frame, but let me phrase the question in a different way.
Mm-hmm.
If you calculate center of mass velocity, how did you do that? So you have acceleration in the global frame from the force plate, basically,
Mm-hmm.
and then you need to somehow get to velocity,
Mm-hmm.
right?
Yes.
So you just integrate it, and then you need some integration constant with that.
Integration constant will depend on the frame that you're looking at. So you need to change the velocity you need to change the velocity or transform the velocity as well. The way that I did was to consider that in the mid stance, the velocity is the velocity of the treadmill time sinus sine of that alpha, or that
I see. Okay.
that slope. Yeah, and the
I
same
see.
thing goes for the horizontal direction as well.
Okay. Okay, so then I think the answer is you did this in the treadmill reference frame, as far as I can understand right now. Possibly.
I think
Right.
it's global reference frame, but
Yeah.
listen, you change the reference frame, you change the forces references to vertical and horizontal instead of treadmill, which
I
is
see.
in
Good.
which is in normal and parallel.
Good. 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 Well, yeah, I was just wondering how to do that because I didn't, yeah, I had to think about that a little bit. And other than that, well, no further questions. I liked it. It was nice. Thanks.
Yeah, thank you.
Ian, please go ahead.
Hey, Arash. I've been thinking lately about the motor unit activation, and I'm wondering if it's been resolved, whether it's an inability to activate all motor units, or if you're actually activating all motor units, but at a submaximal stimulation rate.
Well, as far as I understand is that you're not activating all the motor units, and then you just add more current to the nerve, and you, in that case, you can activate all the motor units.
Are there any
That's
papers
my
that have definitively shown that? Because it seems illogical to me that you have motor units that you're unable to activate at all.
It's also possible, but I haven't dived deep into this in specifically.
Okay, thanks.
Thanks.
Okay, Brent, please go ahead.
So I have some naive, Arash has been listening to my naive questions for the last few weeks, so I have more. Okay, so how do you separate, this term peripheral fatigue and how it might be related to excitation contraction coupling or whatever? How do you separate like that is something that could happen, but maybe structurally you just have damage. Of course you have damage. You have damage to the muscle. So nothing really changes with excitation contraction coupling. Something might just change. Structurally you have damage, more damaged sarcomeres. And so you're just not able to, they don't create force anymore. Does that?
Well, that's basically what we call it peripheral fatigue. So
Okay,
there's
it has
damage.
the peripheral fatigue has to be damage to the muscle. It can't be some change to excitation contraction and coupling that's not associated with damage.
It could also be that part as well, because that's also we call it as we consider it as a peripheral fatigue. So if the excitation contraction coupling also damaged, so there's an impairment, and then that's why we use this doublet sub 10 low frequency and high frequency, assuming that the low frequency in the low frequency we're going to be, and there's a sigmoidal shape. I think I have a photo of that.
Yeah, no, it's okay. I don't.
There's something like there's a sigmoidal shape here, and assuming that their doublet 10 occurs somewhere, 10 hertz stimulation occurs here, the reduction in calcium in this steep part is going to be way higher than this plateau part. So we're going to have more reduction in doublet 10 compared to doublet 100.
Right. So these are just nuances associated with your assumptions of the neuromuscular fatigue assessment. But I'm just trying to understand how one concludes something is damage to sarcomeres versus something is something else that's taking place. And maybe it's impossible to
with this method specifically, it would be impossible. Damage to sarcomere, you probably need a good biopsy of the muscle to specifically look at that, and it's been shown multiple times after eccentric contraction. And with this method, this is just a very like a surface of all that can be investigated.
Okay, and then the other question I had is about the grounded running, the transition towards grounded running, and how it was, the changes were less prominent in downhill running too. But if I remember correctly, those are all normalized to the baseline for the specific condition. So my question is there like a learning effect? Like maybe you start grounded running, not because you're getting damaged, or maybe you're getting some damage, you're getting pain, and you say, I need to start grounded running because it hurts less. And then I'm just wondering if, like, what happens when they come back 3 years later? Do they learn anything? Do they start running grounded right away, and that's why you don't see such a prominent change? Or do they start the exact same way, and because there's a true repeated bout effect, you don't see these changes?
Well, basically, the baseline I actually looked at the baseline, the contact times, step frequency, and flight time, and everything. Basically, I looked at the baseline of downhill 1 to downhill 2. Let's see what happens in minute 1 in downhill run and what happens in minute 1 in downhill 2. There wasn't much difference. So basically, they start almost the same way. Although the interesting thing, I didn't show it here specifically about the impact peak of ground reaction force. The impact peak mimicked this curve, something like this. It went up in downhill running 1. It didn't change in downhill running 2. And it also showed itself in energy absorption as well. And so they started the same way, but they continued differently.
Okay, thanks.
If that makes sense. Thank you.
Yeah, it makes sense.
Okay, Arash, I actually have also a couple of questions for you. But it was a more methodology that you do. So you measure muscle soreness to estimate muscle damage. So my question is that how does muscle soreness could explain the actual muscle damage? Because if I feel my muscle really sore, that doesn't really mean that my muscle is entirely damaged. So do you have any brief explanation that I could get some help?
There are some correlation between the two.
Okay.
Muscle soreness specifically is a very subjective measure.
Yeah.
Even though we quantify it, like based on that Borg scale, we can quantify it somehow, but it's very subjective measure. There is some correlation between the two. There's been a plethora of studies in this field, and it shows that if the muscle is damaged, there is some correlation between the muscle damage and the soreness.
I see. Thank you. Michael, do you have any question to Arash?
Yeah, I have two. Arash, how long does the repeated bout effect last?
In downhill running specifically, based on 1985 study that they did this downhill running, the first downhill running, and then 3 weeks later they did the second one, 3 weeks later they did the third one, and 3 weeks later they did the fourth one. So the second 3 week, so it means 6 weeks later, the effect was the same, almost the same. But
so you don't get much benefit from doing a second bout.
Doing the third bout, basically, you don't get much benefit. But then in the fourth one, which is 9 weeks later, the amount of this protection became very small. So it looks like, specifically in the downhill running talking, this amount of this protection wasn't that much after 9 weeks. But that also go back to the amount of muscle damage that you can actually incur with downhill running, because it's not as much as a single joint exercise. Like if you do like they did that 300 eccentric exercise, eccentric knee extension, the amount of muscle damage is way, way higher compared to the downhill running specifically.
Mhm.
And I assume that it could depend, it could be because of the different workload that you can put in different muscles, because it's not single joints, right, in downhill running.
Yeah, so the idea there is that it's not a novel stimulus. Like they do the first one, you get an adaptation. You do the second bout, you get a bit more adaptation. But because by the third bout of downhill running, it's not novel anymore. That you don't see an adaptation to it.
You don't get much adaptation, no.
Yeah. Okay. So in probably a real life scenario, you're continuously accruing adaptation, because rarely are you running downhill at, you know, the exact same hill every 3 weeks. You know, one day I might run down Lady McDonald, and the next day I might, you know, run down from the top of Cascade Mountain. They're vastly different, right?
Mm-hmm.
And then my next question was, people mostly talk about like eccentric induced muscle damage, but does muscle damage occur with concentric contractions too?
With uphill running, there is some muscle damage. There's another reason for that. For specific, I'm not sure if it is because I don't know much about that, but I know the low frequency fatigue occurs after downhill running as well, and the amount is very high. But then specifically in also isometric contraction in long muscle legs, it's been shown that produces repeated bout effect as well.
Okay, thanks.
Thank you.
Tim, please go ahead.
Yeah, I actually had a question about so the suggestion that it is excitation contraction coupling that's causing the peripheral fatigue. A little bit in line with what Michael just said, like for eccentric contractions, I would think that for a similar force you need less activation according to the force velocity relationship. So then to me that maybe means that you need relatively less calcium or like any type of activation. And so why do you think that fatigue is happening? And is that indeed happening more than for concentric contractions? That seems to me a little bit counterintuitive. And also, do you have any idea like what kind of, like where it breaks down? Is it that the muscle fiber cannot handle too much calcium for a long period of time, or like what is it?
So I don't know a lot about your first part of your question, unfortunately. But about the second part, it seems that the calcium released from the sarcoplasmic reticulum is smaller. The amount is less.
I see. And so is that something that's typically happening with eccentric contractions, or that's just also with concentric? It doesn't matter.
With eccentric contraction, it occurs more. That's what has been shown.
But do you understand that I find that counterintuitive based on the
Yes,
force velocity?
yes, I can't answer that, unfortunately.
Okay, thank you.
Walter, please go ahead if you have any questions.
Yeah, thanks, Arash. I have a couple of questions. Some surprising results that, and you know, obviously people have looked at the repeated bout effect for a very long time, and there's been different speculations. Do you have a speculation based on your result, what you would think the repeated bout effect actually is? Why am I protected the second time from getting as much injury as the first time?
Well, mechanically, it looks like you get stronger muscle tendon units.
When you say stronger, because I remember you had that in your presentation, do you actually mean that I have more strength available? And when you did the strength test with the maximum voluntary contraction, you know, before the first run and then before the second run, did you find a difference in strength of the knee extensors?
No, we didn't find any differences between the two. What I tried to say is that it looks like they can resist more to the same amount of force. So basically they get stiffer.
Yeah.
But again, to just show it, it's just modeling study. You really want to show it, you probably want to do like I don't know, maybe like an ultrasound on the quadricep tendon, looking at it, maybe to make sure that actually happening, just pure mechanically.
You talked a lot about neuromuscular adaptation. Did you measure EMG at all?
No, we didn't measure. We didn't measure EMG specifically. The reason we didn't measure the EMG, and I regret that we didn't. Maybe I don't, but maybe I do, because the protocol was very difficult. People who did this study, and I know some of the people in here, they did this study as participant. It was very difficult to put all the things in part of the participants. I mean.
There's a couple of suggestions that have been made about the repeated bout effect that I think one you mentioned a bit, but I think the other one you didn't. So one suggestion that has been made that when you do eccentric contraction in downhill running, your sarcomeres are pulled onto the descending limb. It's unstable and they get torn apart. And so you adapt by increasing the number of sarcomeres. And therefore, the next time your sarcomeres are not as likely to go on the descending limb. Do you have any feeling about that theory based on your study?
Unfortunately, no, because then you could say, okay, if they increase the step frequency, for example, then you would have had muscles in longer muscle lengths when you touch the ground. Sorry, the shorter muscle lengths when you touch the ground. Then that I didn't see that kind of thing happening in this specific protocol. Mm-hmm. But yeah, I cannot comment on that, unfortunately.
Yeah. I mean, one way that people have looked at, indirectly human muscles, whether there was increases or decreases in sarcomere lengths, is to look at the force length relationship and see if it shifted to one side or the other. But you measured the strengths just at one angle, is that correct?
Yes, yes. Unfortunately, we didn't measure in that sense. There's been studies showing that there was a shift in the optimum lengths.
Yeah. The other theory that has been suggested by some, and you hinted, I think, a little bit at it, is that some people think that in eccentric contraction, you reverse the regular order of motor unit recruitment and you actually recruit mostly the fast twitch and big motor units, but they seem to be more vulnerable to eccentric contraction. And so you actually learn the first time that you should recruit somehow the slow motor units, and that might then actually prevent the damage because they seem to be more resistant to eccentric loading. Do you have any feeling for that at all from your study?
From this study, I don't think I can say anything specific about that, but yeah, that's one of the reasoning behind this neural adaptation theory.
Yeah. And is it correct for me to assume that when you say they were running at 2.8 meters per second for 30 minutes on an 11-degree downhill, that was, from a cardiovascular point of view, for all people, that was a very easy run. Is that correct?
Cardiovascularly, yes, and that's actually the main reason we didn't choose different speeds for different people, because aerobic capacity doesn't limit your performance in downhill running specifically, because at that speed you need around like 30 milliliter of oxygen. Any active person would have 45 milliliter, which is way below that you actually need to do that. But mechanically, yes, that in terms of how much you can absorb, how much muscle damage you can get, that might be different for different people.
So it's safe to assume that your subjects were not like physically tired, but the tiredness was really very directly related to the knee joint and the knee extensor muscles, and that's why you have the decrease in force and those things.
It looks like it. It wouldn't reduce the breathing that much. I did the same study myself as well, and it doesn't look like you get a lot of damage in your muscles. You feel a lot of pain, but breathing wise, you don't. Breathing wise, it doesn't change much. It does, but not that much at the end of the runs.
And I was really intrigued by the result that that in the first run there, if I remember correctly, the contact times increased. Do you also know what happened to the stride length and stride frequency in the first run?
The step frequency didn't change much, actually. We have the results over here. It didn't change much. And also, I should mention that there was a big standard deviation, how people reacted to this specific parameter.
Yeah,
but the step frequency didn't change much compared to the
Okay.
contact time.
So they had longer contact times and thus then presumably shorter flight times.
Yes.
Yeah, okay. And do you have, do you know, do you have any feeling why people did that in the first run?
Well,
Like you said you were a subject as well. Did you do that as well?
yes. The
Okay.
thing is, if you have more compliant leg spring in general, if we talk about, then you have to have higher contact time. It goes down and rebounds and goes back. It takes longer. One way to increase the step frequency, one way is to increase the step. If you want to increase the step frequency, and then you have to, in my idea, you have to recruit more faster motor units. And if we consider that they are primarily damaged during the first phase, then your option is to move to the contact time. And this result is actually the same as the results of 1985 paper, that they also looked at the looked at the step frequency, just the step frequency, and the step frequency didn't change much.
Yeah, I was just really curious. I'm not quite sure why people would do that. Obviously, if you have a longer ground contact time, then your force does not need to be as high to achieve a similar impulse, and then you run downhill. I mean, averaged over time, you need to exert, a similar impulse to kind of stop your center of mass from accelerating down the hill, type of thing. So, yeah, great, thank you.
Thank you.
Benno, did you have any question to Arash?
Yes, I have a more general question. You were introduced that you are going to defend next year.
Yes.
Is the whole thesis related to downhill running, or do you have different parts of the thesis?
One part of the next part of the thesis, now we have more reason to look specifically in the tissue level loading, looking at the bone deformation specifically. And that is going to be, because now we saw, like, just generally speaking, this is just a general bigger picture of the whole, what is happening during this downhill run. So we will be looking at that part as well.
And you said bone deformation.
Yes.
How does that relate to the topic that you presented today?
Not as specifically, it will be related to the biomechanics of downhill running, prolonged downhill running, and what is happening. This is an observation, first of all, right? So what is happening to the tissue level, in the tissue level, assuming that the forces, the moments are in the joint, the moments are becoming smaller at the end of the run. Is it gonna affect the tissue level loading or not?
So you have bone and you have muscles. These are the two parts of the thesis?
Yes. Just the bone, the tibial deformation.
Okay. Thank you.
Thank you.
Ian, do you have any question to Arash?
I do. This one has to do with your upcoming world record attempt. I'm wondering how the repeated bout effect is factoring into your training, and if your pull-up attempts also include an eccentric portion, or is it just you have to pull up and then you can drop and avoid all the eccentric work altogether?
Well, I train myself a lot on not doing too much eccentric work when I go down, to get less damage as less as possible. But yes, this repeated bout effect helped me a lot, specifically in my training, because I did like a very long training, 2,000 pull-ups, and then I stopped for a week to get better, and then I did it again and again and again, getting more and more accustomed to this type of exercise.
Okay, Walter, did you have any question?
Well, a follow-up question to that question. If I realize you want to avoid eccentric contraction, but if you actually do leave your muscles activated, then you get kind of what usually people refer to as a stretch shortening effect. And if you do, I'm not sure if you do, 8,000 pull-ups, but if you do 3 pull-ups like it's actually much easier if I do an eccentric contraction and leave my muscles partially activated and go right back.
Yes, bounce back and forth, yes.
Then completely deactivating the muscles and then reactivating them at the bottom. That would be very bad strategy.
Yes, but then I tried that one too, try to bounce when I go down and go up, like the same way that weightlifters squat, like the Olympic weightlifters squat, they go down and they come back very fast using that stretch shortening cycle. But it maybe it's just me, but it incurs more, it becomes more difficult as you go forward.
And another technical question, in the pull-ups, are you allowed to swing?
Not really. There's very strict measures about that. No.
Yeah, because I have seen gymnasts doing dozens and dozens and dozens of pull-ups, but they do this, like with a very distinct swinging action, and then, in fact, they do a swinging action and then they go directly, on top of the bar from that, not pulling up, but go directly on top with the straight arms. So if you do the swinging action right, then you need much, much less force, but you're not allowed to do that.
No, that's what CrossFit athletes also do.
Oh, they swing, the CrossFit athletes.
Yes.
Oh, they're terrible at CrossFit athletes. Yeah, good. No questions anymore.
Okay, Kun, please go ahead.
Yeah, I just wanted to clarify this discussion a little bit. So just to be clear, Arash will have to do exactly the same amount of positive work as he has to do negative work, right? You have no choice in that, because this is a conservative force gravity. That's one. And I think that the second thing is that what you probably want to do, Arash, is do as little as possible positive and negative work with your muscle fibers. So ideally, if you could construct your arms in a way that there's just a spring, then you can just bounce up and down for free using the spring, right? So I think that the discussion
that's a
should
great
be about
idea.
that. You want to avoid eccentric muscle fiber work, and you want to do as much as possible positive and negative work with your tendons. But you are not going to be able to avoid the eccentric work, right? Because this is a conservative system. That's just all I wanted to add to that discussion.
Yes, thank you.
Sure.
That's also an interesting suggestion.
I love it, Arash, how all these people that can barely do one pull-up give you all this great advice. I mean, me, I'm not referring.
5.
I can do about 3.
I also started with 5.
So
Okay.
when is the competition?
Next Saturday, December 5th.
And how big is the probability that you make it?
I don't know. I will try my 100%.
I'm not sure if you were here before, but he needs to do 7,600. And he said in a training a couple of days ago, he did 4,000 in 10 hours. Imagine that.
You can go to sleep and then come back.
That's crazy. Arash, you're crazy.
Yeah, thank you. I will consider it as a compliment. Thank you.
Brent, if you have any question to Arash.
While Walter's around, I'd like to steer the questions back to this sarcomere damage. I personally don't like the explanation for the repeated bout effect, that somehow you're able to like change the way you recruit motor unit or fast twitch, slow twitch. I don't know why I don't like it. It seems like it's more difficult for me to accept than sarcomere damage. So I do have a question. Maybe this is more for Walter. So if I have sarcomeres in series that are being is it safe to say that I have weak sarcomeres and strong sarcomeres, and that when I start a new activity, especially a new eccentric activity where the force is very high, that the weak sarcomeres are operating on the descending limb, and those get damaged, and then they get sort of also replaced with new sarcomeres that are not weak, like in addition to maybe adding additional sarcomeres. I still don't understand how you add a sarcomere in series to a muscle fibril.
Well, I obviously don't know the answer to that, but the idea of sarcomere addition is not that this would happen as you do the exercise. The idea would be that that happens over, in the recovery period. Yeah. And but I think I would tend to agree with you that that probably is not an important or a big effect, because when we have animals running downhill, the increase in sarcomere number that you get, when you do that for 3 or 4 weeks regularly is minimal. You get maybe 2 or 3% increase. So there appears to be a little bit more sarcomeres, but it doesn't seem to be very many. There's one outlier study there by Dave Morgan, who claims that after 5 days, they saw up to 15% increase in sarcomere number in downhill running rats, but that has not really been confirmed. But maybe, Rob Griffiths is our neuromuscular guy here, and has all the neurophysiology training background. So he might have more of an insight about recruitment and de-recruitment of slow and fast motor units. I do know that there is specific, for example, rubrospinal pathways that can inhibit very specifically slow motor units in certain actions, for example, in very quick movements. But I'm not really sure if that's trainable or anything, but Rob might know more about that.
Yeah, I think that the rotation of motor units that get recruited during a contraction is not, there used to be the pattern that as the stimulus went up, you recruited them sort of like you would recruit electronic circuits, but it's not like that. My understanding is they wander between the recruitments of different motor units, and that changing which types of motor units you recruit later on seemed to me quite a reasonable idea, because I was always, when I first met the evidence that motor units are recruited not in a set pattern, that they wander between different ones, I was surprised, but then I was thinking of the nervous system a little bit more like an electrical system, like wires and things. But it does vary, it does change. The other issue you were talking about, Brent, was about creating new sarcomeres. I gather when you do an exercise that's stimulating laying down more sarcomeres in series, you recruit more muscle pilot cells at the beginning of the muscle fiber, and they lay down a new sarcomere with embryonic form of myosin. So if you actually look at the ends of muscle fibers, if you've been losing and recruiting them, they're embryonic form sarcomeres. So they're readily adapted. There was a lady from Western Australia who did all that sort of work. I can't remember her name. But it's a while since I played with those things.
What I can't understand is, and maybe I shouldn't think about sarcomeres in series as sort of like a chain link, but like what I'm trying to figure out is if you break a chain link, if you damage a sarcomere and then you repair it, I understand that it's not going to be real time. So this happens during rest or whatever. Can you go in and do you replace an existing damaged sarcomere with a new healthy sarcomere, or can you only add at the ends of these things?
I think you're supposed to be able to replace the sarcomere that's there. Otherwise you end up with you would easily be able to see a whole lot of little scarred sarcomeres along the path. And I haven't seen that. But my expectation would be that a quickly repaired sarcomere, my assumption would be that the myosin is going to be embryonic form myosin. And so that sarcomere's immediate properties, I would assume, would be different to the ones either side of it.
And would you suspect that they would be weaker in that state? Like before it's let's call it an adult sarcomere?
I think that's a terrific hypothesis to test. You get non-uniform sarcomeres changes because you've got a weaker one, or in the act of repairing that sarcomere, did you make, well, I can't imagine going along and then suddenly having a fatter single sarcomere. But its myosin properties, I would expect to be different. I would expect them to be the properties of embryonic form myosin.
The one thing to remember, Brent, is always that sarcomeres are not there in isolation in myofibril. They're very heavily connected to neighboring myofibrils, and neighboring fibers are connected to other fibers. And so when you damage some sarcomeres, let's say you would damage 5% or 10% of the sarcomeres, you would not expect a 5 or a 10% decrease in force. In fact, there were a couple of studies that were done like 40 years ago where people cut a muscle halfway through. So they made physically a cut with a knife or a scalpel halfway through the cross-sectional area of a muscle, and then activated it. And they still had about end-to-end 80 or 85% of the force. So when you damage a muscle in that way, there are a lot of cross connections. And then the person in Chicago whose name
Rick Lieber?
No, it was not Rickley, but it was the guy who has been in Chicago for a long time. He worked together with Philippe Maas. They cut the tendon of a soleus muscle in the cat. And so the tendon did not have any attachment at all anymore. But then they activated the soleus tendon and measured the force that was transmitted to the Achilles tendon and found that the soleus that was completely cut at the tendon still had connections that 50% of its original force was transmitted to the Achilles tendon. So there are enormous cross connections between muscles and within muscles that really make this system quite stable. And when you lose a sarcomere, that really doesn't mean, you know, you use that percentage of force.
Okay, would there be any last or final questions, Arash?
Just I wanted to add on to this discussion. As you're talking about this, I was just thinking about the possibility of maybe putting a rat in a medically induced coma and doing a time-lapse photography of damaged sarcomeres after some sort of eccentric exercise and just looking how it recovers and where sarcomeres might be added. Be a huge experiment, but it could be really interesting.
That would be so cool.
Okay.
We did, you know, Ian, I think you were here already when we did those experiments with Maria Yamamoto with the chronic stimulation where presumably, according to what we found in Tabary and Tardieu and other people, you lose an enormous number of sarcomeres in a very short time. And then we wanted to see how the recovery works. And we were looking at how you could identify newly laid down sarcomeres. Like in bone, there are ways of knowing exactly where new bone has been added to the old bone by certain labeling techniques. If you are aware of any of those techniques that would work for newly laid down sarcomeres, which we looked at about 4 or 5 or 6 years ago, and they didn't really find anything, that would be really cool.
As close as I can think is maybe centrally nucleated fibers.
Yeah.
Okay, on that note, I would like to thank Arash again for sharing his work with us, and good luck on December 5th for the big competition. Next week, we will be hearing from Tim van der Zee, and the title of his talk is The High Energetic Cost of Rapid Force Development in Cyclic Muscle Contraction. Thank you for coming today, and I'll see you all next week.